All right, good morning, guys, and we're going to go ahead and start the notes here. We're going to start with section 2 of our notes, which is going to be geometric sequences. We're going to look specifically at the recursive formula and the explicit formula for geometric. Now, remember, yesterday we talked about the arithmetic sequence, which was between each set of numbers, we found that there was an addition or subtraction up. Today we're going to focus on looking at it, and there's going to be a multiplication or a division between each of our terms. Now remember, this is different from looking at a linear function or exponential function, because really we're going to focus on just the y values, just the outputs here. So we've got a little warm up here we're going to start with, and we can see this pattern of dots. With the pattern of dots, there's many ways to look at it, but when I see this, and you may too, I'm going to notice what's happening between the dots, because there seems to be 3 single dots here, and then I've noticed that they've seemed to double into the next sequence. So, and I'm looking at the one next to that at 2 minutes here. So at the beginning, 1 minute they seem to have doubled, 2 minutes they seem to have doubled again. I can see 2 sets of 4, so they doubled again. And I'm going to go ahead and guess that they've doubled here without even counting those, even though I can really quickly. 4 by 4 is 16. And there's 6 here. So it looks like it's doubling between each one. So I'm going to go ahead and mark that down, because that's the first thing that stood out to me. And we've talked about this a little bit yesterday. We previewed that if they have a common number that they're growing by through multiplication or division, that we could call that a common ratio. And that's kind of what we're going to look at today. But let's take another look at these, and not only look at how they multiply up here by 2, but let's take a look at how many are in the sequence of dots. So in this case, at this first beginning spot, I've got 3 dots total. I'm going to look at the next sequence here at 1 minute later, and I've doubled that number of dots, so it's going to become 6. And then again, 12, 24, and then finally 48. So we've got 2 different ways we're looking at the dots, one doubling between each terms, and then we can see the sum of each set of dots at every minute interval after that. So it says describe and label the pattern of change that you see in the above sequence of figures. Again, how's it changing? Well, it's a doubling each time. We're multiplying by 2. So I'm going to keep this short. You guys can write in what you want there, but it's going to go ahead and double by each minute. And again, if I go too fast or if I talk too quick, remember this video will be posted on my website, so you're welcome to go back and watch it and pick up anything that you didn't get. All right, so it says question number 2 with this warm-up, assuming the sequence continues in the same way, how many dots would there be after 5 minutes? So really we're going to look at this pattern here. So we're at 4 minutes. We know it's going to double again. Let me make that relax there. We know it's going to double again. So from 48 minutes, it's going to go ahead and turn to 96. Right? 48 doubled is 96. So it should be 96 dots. It was a little quick after 5 minutes. So I'm going to go ahead and write 96 in there. All right. Now they're going to want us to turn it into a table. Okay. So we can kind of get the comparison between the exponential function we know it is and kind of getting this sequencing concept on our head. We're going to tie these 2 together. So looking at the initial amount of dots at 0 minutes, which haven't changed yet, which means it's going to be 3. And then we're just going to write that sequence down that we kind of recorded at the top. It's going to double between each time. So there's 12, 24, double again, 48, double again, 96, and then at the 6th minute, we're going to have 192. So there's a sequence of events. We could attempt to write a linear exponential function there. It says graph the points. I'm going to save some time. I'm going to kind of rough it in. This is just a sketch. Normally we wouldn't do this, but for time's sake, for this video, I don't want it to go too long. There's a really rough estimate of what it would look like, without giving it a scale or anything like that. If I was in class, we'd do that a little bit more precise, but for this section of notes and keeping our speed up, because we don't want to take too long on video notes, we know how that goes. It says write a recursive formula to describe how many dots there will be after t minutes. And here it says recursive, and we're kind of familiar with that. We said this is a way to write a formula that's based off the previous term. So a couple of ways we could look at this. We could even use function notation if we wanted to. So f of t, where's the function at t minutes? We could look at it as saying our previous term times 2, or we kind of learned a little bit, we didn't get into it a lot, we could look at, instead of saying previous, we could look at it in the sequence of events and say that we could take whatever term we're looking at, so a to the t minutes minus 1, that's the way to describe previous, right? We subtract 1 off of whatever term we're looking at. This would indicate the term before times 2. That would give us our next term. Okay, so these mean the exact same thing. This is just a notation to kind of write it. This is just in words, so you can kind of see it there. And again, that's a recursive look. Now we're going to look at the explicit. So explicit is something where we can, not necessarily based off the term before it, that we can kind of jump around the sequence anywhere we want. It's a little easier to use. The recursive is a little easier to write. So if we keep the function notation here, we'll say f of t equals, and then again, remembering that they're a multiplication of 2 between each of these terms. And if we wanted to go to t units down the way, however far t was, we would take 2 and we'd want to multiply that t times. But if we multiply, that's really an addition. So we don't want to multiply. We really want is 2 times 2 times 2 times 2 times 2 t times. And anytime that we do this, we multiply these together, it's really an exponential form. So 2 to the t. But when we look at that a little bit closer, we don't actually want it to be t, we want it to be the previous term multiplied by 2, so we get that term we want. So when we write this out, it's going to be 3, because that's our initial amount, and it's going to be multiplied by 2, because that's what it's growing by, to the t minus 1, which is the previous term. So that would fill out this explicit form for this function. So let's look at that a little bit more, now that we've kind of had a little warm up with it. All right, I'll change back to red here. I think I have red. All right, so if a sequence of values follows a pattern of multiplication, each term, multiplying each term, by a fixed amount, not 0, because 0 would make it really boring, it would just become 0, times each term to arrive at the following term is referred to as a geometric sequence. So this is, again, a multiplication between each term that we have in our sequence. The number multiplied each time is constant. That's key to verify that this is a geometric sequence. All right, so as we talked about a little bit yesterday, that fixed amount that is being multiplied is called the common ratio. Let's see if we can get that right. Common ratio. Again, we're familiar with this term. I'm going to give you the notation for it. Notation is R for common ratio. This common ratio referring to the fact that the division, again, fraction of the second term to the first term. So let's write that out just so you can see what that's talking about. So it's saying take the second term, divide it by the previous term. And again, we would do that down the sequence. If this is common, and if that's common multiple. So to find the common ratio, we're going to do that. Ooh, let's see if we can clean that up a little bit. Sometimes it's hard to talk and write quickly on this thing, so bear with me. So that common ratio, divide the second term by the first term. Again, y2 divided by y1, or y3 divided by, or y2. So, and then keeping that there in the pattern. So if we're going to use that idea there on the next example here, it says, is the given sequence geometric? If so, identify the common ratio. So we're going to do kind of what we were doing up top, and we're going to go ahead and take the second term, so 15 here, and we're going to divide it by 5, which that's not too hard to do in our heads. We're going to find out that it's 3. And we're going to continue that pattern all the way down. 45 divided by 15, again, it's 3, and then 135 divided by 45. Without a calculator, I'm just going to tell you that it is 3. So when we found that this is constant, we found two things. One, we found R, which is the common ratio. And then 2, we've also verified that it's a geometric sequence. So let's write that down. So it is a geometric sequence, and our r is 3. So if we look at example 2 over here, we're going to go ahead and do this same thing, divide 30 by 15. And we can all handle that, that's 2. But if we divide 45 by 30, we'll notice it isn't 2. It actually comes up to be 1.5. And then if we continue that pattern, again, with the aid of a calculator here, it's going to come out to be 1.33. So this is not geometric, and there is no r. Okay? So the next two examples are pretty much the same thing, except for it has you find the next term. I don't think we need to spend any time there, because I think we're okay with multiplying by whatever the geometric sync is to find the next one. So here it is. The recursive form of a geometric formula is kind of similar to what we were dealing with the arithmetic, is we need to identify the first term because we got to see where a sequence starts. And then again, just make sure this is recursive, so it's going to be based off of the previous term. So whatever term we're looking for, so a to the n, that's just a way to say, hey, this is a sequence, and we want to find the nth term. You're going to take the previous term, n minus 1 indicates the previous term, times whatever that geometric common ratio is, so times r, and that's for the recursive. If we look at the explicit form, we would, same thing, this is just signifying that we're identifying nth term in this sequence. It's going to be times the first term. Let me erase that because it looks like I wrote on it to change it. So this is your first term. Again, it's identified in the recursive, but the explicit, we actually put it in there. So the first term multiplied by the ratio to the n minus 1, which is the previous term. So we're multiplying the ratio to the previous term. That's kind of what's happening here. Okay, again, a to the nth is the nth term, n is the number of terms, r is the common ratio. So if we want to look and do one of these, let's take down here. Okay, so it's describe. We're basically going to fill out these. So we're going to find the next term, we're going to write a recursive rule, we're going to find the nth term, and we're going to write an explicit rule. And then we'll be done with the notes for today. So we got to do this, we're going to take a look at these y values. We're going to take the second value and divide it by the first value. So 10 divided by 5 is 2. 20 divided by 10 is 2. 40 divided by 20 is 2. So we can see that we've got ourselves an r. And that, again, that verifies that it's a geometric sequence, and we know what our common ratio is. So if we really wanted to find the next term, which is what it's going to ask us to do first, we're going to take 40, we're going to double it. I think we can do that in our heads. That's going to come out to be 80. So we'll write that over here. So the next term is going to be 80. So now we need to write a recursive rule. Right off on the side, just so we're used to it. This is just set notation, meaning that there's two parts to our recursive rule. The first part then is the first term. So our first term in this case is going to be 5. So a to the 1 equals 5. And then we're going to write to the nth term. Remember, we can write it two ways. We can say previous, as in previous term, times whatever our multiplier is, so whatever it's being multiplied by. In this case, it's doubling, so we can write previous times 2. Or we can write the same thing, and this is really where we want to be. A to the n minus 1, indicating the previous term, times 2. So either one of those can be put inside of here. Okay. If we're working on a line, I'll just show you this. If you're working on a line, you don't actually have to write the system notation. You can use a little semicolon here to separate the two. If you can't squeeze it in there, or you can see I put it off on the side. So there's our recursive rule. Again, not very fancy, it's pretty self-explanatory, but it's always based off the last term, so it's pretty limited. Now we're going to find the nth term. So if we can see that we multiplied to get the second term in our sequence here, here's our first term. To get to our second term, we multiplied by 2. To get to our third term, we multiplied by 2. But notice that our multiplication here is always 1 behind. So to get to our second term, we've multiplied by 2 once, right? And to get to our, again, multiply by 2 again, to get to our third term, we've multiplied by r twice. So notice how it's lagging behind. That's where that n minus 1 comes from. Just kind of wanted to point that out there. So for our explicit rule, we're going to get down here, and we want to get to this nth term. Well, we're going to multiply by 2 n minus 1 times, because whatever this number is, we're lagging one number behind looking at this, okay, looking at the number of times we multiply by 2. Just a little reminder. So if we're going to write it, a to the n, again, equals our first term, so 5, times our rate, our common ratio, which is 2, and to the n minus 1 term. And that takes care of our explicit rule. Now there's some other examples down here, but I don't think I want to go into too much detail because that's really where we spend our time. And then when we get back, or when I get back, whatever day it is that I next see you, so I'm assuming Tuesday, we'll review these examples a little bit more. But this is pretty much all that you need right here. You need to be able to write the explicit, right? The explicit term, and the recursive form. The recursive is almost so simple that some people will try to mess it up. It's really basic. The previous term times r. And again, the explicit looks very similar to our exponential function that we're familiar with, right? A times b raised to the t. Very similar to that. But again, previous term n minus 1. All right, guys, your homework is the worksheet right behind, and I will see you tomorrow.